I want to show you the formal definition of the limit, and I want to show you how to compute a couple limits with it. So let's get to it. So we know the informal definition that if I want to say the limit as x goes to a of f of x, and if I want to say that's equal to number L, then you can imagine some function f of x and if I pick some number x equals to a, and I want to say the limit is equal to L, and I've drawn a continuous function here, so the limit will be equal to f of a, which will also be equal to L. So you've got the graph, which is the x value and the y value, y equals f of x together. And then on the x-axis, you've got the x values, and on the y-axis, you've got the y values. And so your y values are the things that are limiting to L. So that'll be like the number L. And this would be the point a equals x and y equals L. And if you want to informally say the limit as x goes to a of f of x equals L, then what you're saying is that if the x values are close enough to a, then the y values must be close to L. And let's start to formalize that. So saying the x values must be close to a is the same thing as saying, look, there's going to be this interval that maybe it's very small, but I'll draw it so you can see it. There's going to be this interval of x values around x equals a with the following property. So if you're in this interval, then the y values also have to be in a corresponding interval that's really close to L. And let's look at what it is on the picture. So if you look at this x value, if you look at that point in the graph, you look, what's the range of the y values? Basically, it's going from here to there. So it's basically almost right here at L, and it extends upward to this higher point. So if you're in this range, then you have to be in that range. But to make this a little bit more formal, what you do is you say, I get to specify, or you get to specify, how wide this interval around L is. And once you make that specification, then there's going to be an interval of x values, such that whenever you're in that interval, the y values have to be in the orange or the yellow interval. And so let's do that. Let's turn that around for a second. Let's illustrate the process I just described. So I get to pick an interval around L. It could be big or small or whatever. Typically it's very small, but I'll draw it large so that you can see it. Let's pick this interval. I'm losing my y-axis a little bit. So let's pick that interval. So I need to say now that there exists an interval around x equals a, such that whenever those x values are in that interval, the y values have to be here in yellow. And you can sort of visually see it because, well, there's no restriction up here because none of these y values are getting bigger. What about down here? Well, here's the restriction because the y values can't get lower than this. So I can't let my x values go beyond that point. But if I do kind of cut it off here, and I can pick anywhere on the other side, as long as x stays in that range, then my y values stay in that specified range. But now if I pick a smaller interval for L, like that interval, then I'll need a smaller interval around A, because now your y values can't go up any farther than that, and your x values can't go down any farther than that. So it looks like the top part is kind of restricting us. So I get, I get this smaller interval around x equals a. So what I need to do to write down the formal definition of the limit is to write a precise mathematical statement that kind of conceptualizes this. And so here we go. So I'll write it down piece by piece and then explain it as I'm going. So the way you start out with this is you say for each positive number bigger than 0, and it's common to use the Greek alphabet here, so you say for each epsilon bigger than 0. And so where is this on the picture? Let me erase 2 of these so I've just got one interval. The epsilon is you picking the width of this interval. So here's epsilon in the picture. So epsilon bigger than 0. Epsilon is like the width of this vertical interval. We say there is another width, and we use the Greek alphabet again. We call it delta. It's a delta bigger than 0. And delta is nothing but the radius or the width of this interval. And actually, this interval doesn't have a as its center. So what you would do is you'd take the smaller of these widths and then go out here and do it like that. And then you get a real interval with a as the center. And so this is the radius delta, or the width delta bigger than 0. So for each interval that you pick here, there's a different interval around your x values. So that whenever you're inside this interval, the y values are inside that interval. So how can I write that down mathematically? The way I'm going to do it is I'm going to say, well, if x is inside this interval, in other words, if the distance from x to a is less than delta, that's what width delta means. The distance from x to a is less than delta. Distance from x to a is just the absolute value of x minus a. So if you're inside this interval, then the y values have to be in this interval. And the y values are f of x and f of a. So the distance from f of x to f of a has to be less than the radius that you specified. And so that's the formal definition of a limit. It's kind of a mouthful. So for each epsilon bigger than 0, there's a delta bigger than 0, so that if the distance from x to a is less than delta, then the distance from f of x to f of a is less than epsilon. You think of it by saying you can pick any interval you want about the limit L, and there must be a corresponding interval about a, so that whenever the x values are in that interval, the y values are in this one. And that's the formal way of saying that the y values will be very close to L whenever the x values are close to a.